When solving word problems like this one, it's often a good idea to put the problem in terms of equations. So let's start by doing that with our kinematics equations, or our projectile motion equations. Remember that the y position is always equal to negative 1/2 g times the time squared plus the initial velocity in the y direction times time plus the initial y position. And much more simply, the x position over time is equal to the initial velocity in the x direction times time plus the initial x position. So how do we simplify these down so we can work with them better? The first thing we can notice is very simple. We're just going to say that the ball starts at 0, 0, meaning that our initial x position and our initial y position are both 0. So that means that we can erase these terms because they're adding 0. So that'll save us some headache. And additionally, while we're erasing here, we can notice that our velocity, or our y velocity rather, is equal to 0 because we're not, our initial y velocity is equal to 0 because we're only being pushed horizontally. So this term also disappears. So now we have these rather nice equations, and also just to simplify it, we'll write this just as v because it's the only velocity we're really going to deal with. So just vt. Okay, still this can seem a little impenetrable. If we were dealing with a flat surface, we could just set this top equation equal to something, and that would save us a lot of time. We'd just solve for t and we'd be done. However, we're not dealing with a flat surface, so how far down the ball has to go before it hits the ramp is dependent on its x position. If it's a lower x position, if it's further to the left, it doesn't need to go down as far. So as we go to the right, we're going down more, but also how far down we have to go in order to hit the ground is also going down. So how do we remedy this? Well, let's look at slope. Slope is rise over run, right? So what does rise over run mean in this situation? Well, rise is how far we've gone, is how far down we've gone. It's going to be a negative number, right? So rise is this, right? If the ball's traveling this way and it's going down, it's going to be that. And the run is how far over we're going. Now we want to deal with the slope, or of the hill, and we want to solve for this in terms of theta. So how do we solve for this in terms of theta? Well, we know that the slope rises this much, or rather falls this much, and that it goes over this much. So how do we find this ratio? Well, it's actually quite simple. If we look at this as a right triangle, which it is because these are horizontal and vertical directions, this is going to be the opposite side, and this is going to be the adjacent side. So if we take tangent of theta, this is going to be our rise over our run. We have to be careful though, since we know it's going down, the slope is going to be negative. So this is our negative slope, and of course that means that negative tan theta is our slope. Perfect. So now we have negative tan theta solved in terms of slope. Now we can look at slope equals rise over run, and these are going to be our y and x positions. So we know that our rise is our change in y, and we're looking at, remember that 0, 0 is the starting point of the ball. So our change in y as we go down the slope is just equal to negative y, right? And or just equal to y, because we started at 0. Wherever we are right now is how far we've traveled. And similarly, our run is our delta x, but because we started at 0, this is just equal to the x. So why is this useful? We want to solve for the y position of the slope, how far below 0 the slope is at a given x position. Actually, we even want to solve for it at a given time of the ball's travel. So if the ball is here at time t equals 1, let's say, we want to solve for how far below 0 the slope is. Say it's at negative 3, right? And then at t equals 2, the ball is down here, and the slope is now at negative 5, and it's getting closer and closer. So we want to find what position the slope is at under the ball at a given time. So we know that slope now equals y over x. This y is important to notice. It's not equal to this y. This y is the y of the ball. This is the height of the slope. So let's call it y slope. I know it's confusing to have two slopes, but I think it's pretty unambiguous. Okay, so y slope over x, and I'm using the same x because the x of the ball is the x we care about, is equal to negative tan theta. Okay, so what moment in time are we looking for? We are looking for the moment in time where the ball hits the slope. That is, that y slope, the position of the slope under the ball, equals y ball t, right? Which is our expression up here for y of t, the expression up here. So we can set these two equations equal to each other. We know from this we can simplify and move the x over, that negative tan theta x equals y ball, which is negative 1/2 gt squared. Now, we have this x term here, which we want to solve for in terms of t so we can isolate it. We don't want to have an x in our equation. But remember, from up here, x of t, this is the same x from up here, x of t is equal to vt. So we can quite simply just plug that in and get negative vt tan theta equals negative 1/2 gt squared. Now we just want to solve for t in terms of everything else, and this isn't too bad. We'd cancel out the t here and here, so we're left with just this, and then we move the g and the negative 1/2 over, and the negatives cancel out. So in the end, we're left with negative 2v tan theta over g equals t. Lastly, we're asked to solve for the x position of the ball when it hits the slope, not the time. But remember that our x position is just velocity times time. So we just plug in this t into that equation and basically just multiply it by b. So our final answer is negative 2 is x equals xf for final is negative 2v squared tan theta over g. And that's how you find this.